Pluto is a faraway, mysterious, and prominent planet that was once considered to belong to our solar system. Despite recent groundbreaking assertions from well-known physicists like Michio Kaku and Neil deGrasse Tyson, Pluto has been reintroduced to public discussion. They have suggested that this icy planet may be heading toward a possible collision course with Neptune. However, how could such a situation exist? And what would be the repercussions of such a historic event? Are we observing something unusual and unpredictable, or is there more to it? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, once thought to be a planet, was reclassified as a dwarf planet. However, it continues to be a subject of fascination and study in the vast universe. Leading experts have suggested that Pluto's orbit is alarmingly close to Neptune's. Astrophysicists like Neil deGrasse Tyson and Michio Kaku have warned that a disastrous collision between these two celestial bodies could pose a significant danger to Earth. But how could Pluto even be involved in such a collision? Pluto's orbit is distinct from any other planet in our solar system. It takes an incredible 248 years to complete one full orbit around the Sun. Since its discovery in 1930, Pluto has yet to complete a full revolution. But the intrigue does not end there. Pluto's orbit is highly elliptical, deviating significantly from the nearly circular orbits of the major planets. One of Pluto's most fascinating orbital features is its interaction with Neptune. For roughly 20 years per orbit, Pluto actually comes closer to the Sun than Neptune does. This raises an obvious question. Why hasn't Pluto collided with Neptune? The answer lies in the forces of gravity exerted by other planets. Following Pluto's discovery, astronomers sought to understand its peculiar orbital behavior. Unlike the other planets, which have orbits that lie close to the solar plane, Pluto's orbit is inclined by 17 degrees. This makes its trajectory more erratic compared to the more predictable orbits of other planets. Despite this, Pluto's path remains stable, illustrating the complex dynamics of celestial mechanics. Specifically, the three-body problem involving the Sun, Pluto, and Neptune. Gravity plays a crucial role in this scenario. Pluto and Neptune are always positioned at least 90 degrees apart whenever Pluto enters Neptune's orbital region. This spatial separation prevents them from colliding. Another stabilizing factor is orbital precession, a slow vertical movement of a planet's orbit. When Pluto comes closest to Neptune or any other massive planet, it is significantly above their orbital plane, adding another layer of protection from potential collisions. Another key concept in play is wobbling, named after researchers who studied how celestial bodies interact gravitationally. Pluto's wobbling effect helps maintain its long-term orbital stability, even though its path appears chaotic. Neptune and the Sun's gravitational influences ensure Pluto remains in a relatively smooth orbit despite its irregular shape. Understanding Pluto's relationship with Neptune is essential to grasp the overall stability of the solar system. Computer simulations from the late 1980s demonstrated that, despite Pluto's erratic orbit, stabilizing forces prevent significant deviations over time. These simulations also showed that Pluto's orbit remains stable for millions or even billions of years. To fully comprehend the gravitational dynamics between Neptune and Pluto, we must also consider the influence of massive planets like Jupiter and Saturn. Neptune's gravitational pull keeps Pluto's orbit in a unique resonance. Every time Pluto completes 2 orbits around the Sun, Neptune completes 3. This resonance helps maintain Pluto's stability. Additionally, Jupiter's immense gravity plays a crucial role in keeping Pluto's path in check, while Saturn further contributes to this dynamic balance. Together, these forces ensure Pluto continues on its current trajectory, potentially for millions of years, preventing it from being ejected or colliding with another planet. Without these stabilizing forces, the solar system would be far more chaotic, with planets possibly colliding or being thrown out of their orbits, leading to catastrophic consequences. The possibility of a Pluto-Neptune collision highlights the complexities of celestial mechanics and the importance of studying orbital stability. By understanding these intricate dynamics, we gain deeper insight into the workings of our solar system. Despite Pluto's seemingly chaotic orbit, It remains a testament to the delicate balance of gravitational forces. Space exploration frequently leads to unexpected discoveries, and Pluto's irregular orbit is a prime example of the universe's mysteries. The concept of orbital chaos shows how a celestial body's trajectory can be highly sensitive to its initial conditions. Even a tiny shift in Pluto's position or velocity could significantly alter its orbit over the long term. Advanced simulations have been invaluable in helping scientists understand these interactions, demonstrating how Pluto and Neptune influence each other through their gravitational pull. These studies continue to reveal the hidden forces that maintain order in our vast and dynamic solar system. Small changes in conditions can significantly influence Pluto's traversal of its orbit. Pluto's orbit is stabilized by libration and other mechanisms. Simulations of precession have also been used, revealing that Pluto's orbit is extremely regular. However, minor deviations from its initial circumstances can lead to significantly different results, making long-term predictions about its movement difficult. Despite the apparent chaos, Pluto's orbit remains fairly stable over geological timescales, billions of years, indicating that there is order amidst what appears to be chaos. An underlying pattern exists in Pluto's motion. Predicting celestial movements, particularly for irregular orbits like Pluto's, is a massive challenge due to the inherent unpredictability of such systems. Any long-term forecast contains uncertainty. Numerical models support our efforts to comprehend and anticipate these movements. However, their accuracy is heavily influenced by exact initial conditions. Even the smallest error can lead to completely different outcomes, making it difficult to predict Pluto's future course with confidence. In contrast to the chaos of planetary orbits, Pluto's story serves as a reminder of the dynamic and ever-changing nature of the universe. Despite numerous advancements, our comprehension of Pluto's unique case in space demonstrates how much we still have to learn about gravitational interactions and their impacts on celestial bodies. Pluto's orbit provides important insights into the workings of the solar system, depicting how the location of every planet can significantly impact the stability of others. This raises the question, why does Pluto stand out? Astronomers have expressed concerns about the possibility of Pluto colliding with Neptune. However, despite these factors, Neptune has remained stable. Neil deGrasse Tyson, one of the leading astrophysicists responsible for Pluto's reclassification from a planet to a dwarf planet, offers a valuable perspective on the mysteries of Pluto's orbit. Tyson has significantly shaped the public's perception of Pluto and its place in the ever-evolving landscape of astronomy. He examines Pluto's reclassification not as a loss but as an important modification based on our expanding understanding of space. Tyson's approach to celestial bodies and orbital mechanics reflects a view that discovery and evolution go hand in hand. He sees Pluto's orbital complexities as indicative of how much more we have to learn about the universe. Despite the uncertainties, he remains hopeful about the study of Pluto and the potential implications of its movements. One of the biggest questions remains: will Pluto ever collide with Neptune, or is this just a brief confusion in an ever-changing cosmic system? Answering this question requires further study. For now, we are left with even greater curiosity about the unknowns of our solar system. The possibility of a Pluto-Neptune collision invites deeper investigation into the forces that govern planetary motion. A collision between two celestial bodies with vastly different characteristics raises intriguing questions about gravitational interactions and their influence on the solar system's development. If Pluto and Neptune were to collide, the effects would be significant, not only for understanding planetary behavior but also for studying the solar system's long-term evolution. To understand the dynamics of a possible Pluto-Neptune collision, one must consider the characteristics of both planets. Despite its designation as a dwarf planet, Pluto contains a variety of frozen compounds due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere is primarily composed of nitrogen, methane, and carbon monoxide. In contrast, Neptune is a massive gas giant composed mainly of hydrogen, helium, and other lighter elements. A collision between these two bodies would undoubtedly have a major impact, potentially triggering events visible across great cosmic distances. However, Neptune's gravity is not the only stabilizing force at play. Jupiter, the largest planet in the solar system, also exerts a substantial gravitational pull, contributing to Pluto's stable orbit and preventing it from coming too close to Neptune. The gravitational relationships between planets in the outer solar system make a catastrophic collision between Pluto and Neptune unlikely. While Neptune's gravity plays a role in maintaining Pluto's orbit, the interactions between other planets, such as Saturn and Jupiter, further ensure Pluto's stability. Additionally, Pluto and Neptune are in a gravitational resonance. Pluto completes 2 orbits for every 3 of Neptune's. This resonance creates a natural barrier that prevents the 2 planets from colliding. Often described as a gravitational dance, this mechanism ensures that while Pluto and Neptune's orbits cross, they never result in a collision. This extraordinary balance demonstrates how celestial bodies maintain harmony despite the complex forces at play. However, even this equilibrium is not guaranteed. Small shifts in planetary positions or velocities, caused by external forces such as a passing star or an undiscovered celestial body, could disrupt the resonance and lead to unpredictable outcomes. Studies of Pluto, Neptune, and other solar system objects are crucial for understanding their long-term stability. As technology advances, researchers will be able to refine models and gain a better understanding of the forces at work. New data may reveal whether Pluto and Neptune's delicate balance will hold or if unforeseen influences could alter their connection in the future. One emerging possibility is the existence of an unidentified celestial body, sometimes referred to as Planet 9. Some scientists theorize that this hypothetical object, located in the far reaches of the solar system, could exert gravitational forces that subtly alter the orbits of planets like Pluto, potentially redirecting them over time. While Planet 9 remains speculative, its potential influence adds another layer of complexity to the already intricate web of gravitational interactions. Beyond planetary interactions, it is important to consider the broader context of the solar system's evolution. The Sun itself is slowly losing mass due to solar wind, which could cause all planetary orbits, including those of Neptune and Pluto, to gradually expand over time. Such changes might affect their relative positions and influence their long-term stability. The outer solar system is not a static environment. Comets and other small bodies constantly move through it, exerting their own gravitational effects. Though rare, such interactions can occasionally perturb the orbits of distant planets like Pluto. Over long periods, the cumulative impact of these forces ensures that Pluto's orbit remains dynamic, constantly evolving in response to the gravitational interplay between celestial bodies. On a more speculative note, large-scale cosmic events, such as the collision of smaller objects in the outer solar system, could also disrupt planetary trajectories. If such an event were to occur, it could trigger a chain reaction, altering Pluto's motion in ways we cannot yet predict. This highlights the chaotic nature of celestial mechanics, where seemingly minor influences can lead to major changes over time. Understanding these potential scenarios requires advanced simulations and continuous observation. As our knowledge of Pluto's orbital behavior improves, the future course of its movement will become clearer. The ongoing study of Pluto, Neptune, and the outer solar system remains a key focus in modern astronomy, offering insights into the gravitational forces that shape our cosmic neighborhood.